harmonic space for any p from 1 to infinity, including infinity. Let's use some of the basic properties of LP spaces. Let's see how many of them we can do in the remaining time. So begin by the first property that basically says that simple functions are dense in LP. They are dense in LP. Now, what would be the consequence of this result? This result that you want to have a integral function that is in LP spaces, and you can always find a sequence, or you can approximate it by the sequence of the simple functions actually in LP sense. This gives you advantage in any calculation. In other words, sometimes we want to show a property for entire space, for example LP space, then we can run kind of a density argument which simply says that if the same property is true for dense subspace of some that space, then that would be true for, or you can extend it to the entire space set. So we did something like similar in function analysis as well. So dense subspace is important. So the theorem says that consider a set that is collection of the maps from X into R or maybe C, doesn't matter, that is S is simple, and obviously you want it to be measurable. We also want one property true actually, that this is a kind of a simple function for which the collection of the points for which this simple function is non-zero, okay, has a finite measure. Okay. So it's a collection of, so this S is the collection of simple functions such that they are measurable, and the collection of the points which has measure non-zero, the collection of the points where the function is non-zero must have a finite measure. And then what we can show is that then for P between 1 not including infinity, this is important, between 1 and not including infinity, then this S is dense in LP. Okay. That's the basic property. This simple, it's not that difficult. So what we can show, first of all, we need to show that S indeed is contained in LP. Let's show that S is a part of LP, LP space actually. Okay. So in order to show this, that this is true, since following is true, that if you take any S from here and you integrate it over X, then I know that this S takes some finite number, so it takes some values out. So it takes some finite number. So in other words, S must have a maximum value in it. X must have a maximum value. So if F has a maximum value, then S power P must have a maximum value as well. So in other words, I can say, by the way, I can break this X first down into two sets, collection of the points where S of X is not 0, plus, collection of the points where S of X is 0. Okay, so that's the first thing that I can do. But this will be for sure 0. This will be the interesting thing. So I can estimate this guy by the maximum or the supremum of S to the P. Okay? And du over this set X such that S of X is not 0. Are we happy with this? And this is going to be a fixed number. This is going to be a fixed number. Because if it takes, so it's like you have a finite set. S takes values from a finite set, and from that finite set you must have a number that is bigger than other. So that number is bigger than other. So this is like a constant number, so I can pull it out of integral, and I'm going to get what? Maximum of Fp times the measure of X such that f of X is not 0. And both things are fine. Okay? Both things are fine, so this must be fine. So what this shows that every S is also sitting inside. The key thing that we need to prove that if I take an element here, I can find a sequence from S that approximates. For that, let me take, say for example, an F from LP mu such that F is not negative. Okay? F is not negative. Then by our approximation theorem. So if F is in LP space, then it must be measurable actually. And that's the first condition that we need for F to be in the space actually. So it must be measurable and non-negative. So there exists a sequence of increasing sequence of the simple functions. Okay. We have this approximation theorem. Sequence of simple functions. Such that when k goes to Fk is that, right? Point 1. And by the way, this sequence of simple function is increasing as well. So it's increasing sequence of the simple functions. Now it is increasing, so it's increasing to F. So F is kind of a, so it's kind of dominating all the elements of this increasing sequence actually. So I can say that since Fk is less than or equal to F, okay. So by the way, on this sequence you can say that is it necessary that this sequence must also be in, what do you call LP mu? Okay, they are simple. Okay, but we need those simples which are also in LP mu actually. So we don't want to just take simple functions from outside which can approximate basically. So Fk is less than or equal to F, so Fk power P must be less than or equal to F. Okay? And therefore, I can integrate it. This must be finite. That is, all of these Fk's are from LP. Okay. what we have shown? We have shown that in Sk, I have simple functions that are pointwise converging to f. But I need to show convergence in LP sense actually. So that's what is our EM. So you just don't have to show the convergence pointwise or something else. You just have to show the convergence in LP. So convergence in LP means, convergence in LP normal. Okay, so that's the last thing that we would like to show. By the way, one more remark also before showing that Sk indeed converges to f and LP norm is basically this, that if you have f minus this SNP or SKP, this must be less than or equal to so I'm treating, so we showed actually that these simple functions must be in LP space, and now I'm making an observation, and that observation is, so it's a really tiny and interesting part actually. The observation is that f minus this simple function and its pth root is less than or equal to this. Okay? Now I am treating this entire quantity as a sequence. So I'm treating this as, for example, as Gn actually, some Gn. Okay? And I am treating this function, like this expression, as the function g that you have in Lebesgue dominated convergence theorem. So I'm not bounding this sequence that is going to converge to what? Converge to 0, because Sk is converging to f. So this sequence f minus s and p is going to converge to what? 0. And this sequence is bounded by a function. That function is not f, it's f power p. And since this f is in LP, so this means that this guy, fp, or its pth root is finite, and hence this guy is finite. So I can treat this entire function as an element in element mu. Not f, but this f to the p in element mu. So since f is in LP, so this must be finite, and if this is finite, so this guy is in element mu. And this sequence that I have given named Gn is dominated by this function g. And from this convergence, this Gn is converging to 0. So the Lebesgue dominated convergence tells you that the integral of Gn, which is basically integral of f minus Sn raised to p d mu, would converge to what? Would converge to the integral of 0, which is, which is going to go to 0 as n goes to infinity. And that's what you wanted. Because this is what? That's the p norm of, okay, this is the f minus p norm of the p power norm of the basically Sn. Is it making sense? So what does this show is that this space of increasing function is dense in dense in LP. Next, should ask some of simple properties of LP space. basically spaces which are dense in LP. For example, the space of the continuous functions, okay, which are less elementary than simple functions, the space of the continuous functions with the compact support. Okay? They are also the compact support. Yes, should be. Yes. So the space of the continuous function with the compact support, okay, is also dense in LP. Okay. Not proving it, but that's another space actually. But you need to have one assumption. So it's like this is true in general no matter what x is. Okay? But this is going to be dense in LP, not for all x, but for the x which are locally compact. And by locally compact, I mean in this space, every point, topologically, every point has a neighborhood that is compact. Okay. And by the way, manifolds are also locally compact spaces. So we haven't encountered that true definition. Therefore, you can have LP spaces of manifold as well. Okay. So that you can do this analysis of manifold as well. Anyway, there are more results, but I'm just restricting myself to the things that we can cover this limited time. If we assume that X is a finite measure space, see that these are just bunch of results. So X is a finite measure space. Okay. Then following thing is true. So if P is bigger than or equal to 1 and less than Q and less than infinity. So in other words, I have two numbers P and Q, where the P is bigger than or equal to 1 and P is less than Q, and both are finite. Then you have this interesting relation that LQ is contained in LP. So this inclusion result actually. Okay? So if X is a finite measure space, then LQ is contained in LP. Okay? So in other words, the bigger index you have, the smaller the space is going to be. Okay? So if I take the integral of f and I say that I have fp times 1, and then I apply the Holder's inequality with the exponents p and q. Okay. So if I apply the Holder's inequality, and I'm applying the Holder's inequality in this manner, okay. By Holder's inequality, this is less than or equal to f. So you already have a power p here actually. So you have to be careful. It's not going to be as simple as we saw previously. So f and pq by p. Okay. Everything goes on with p over q. mu of 1 minus P over Q. So can you guess the exponents? What conjugate exponents we are using? So this would be 1 over P and 1 over Q, then this would be, in the standard format. Think about it, what we have done. So, what is the standard? Let's compare it with the standard order inequality. What's the order inequality? Order inequality tells you that if you have Fg, then and you have two conjugates, okay, like a P and Q number, P and Q are maybe A and B, R as S. So 1 over R plus 1 over S equal to 1. Okay. So then this would be same as F R and 1 over R and G S over 1 over S actually. So that's the standard inequality. So here's the thing. What is R here? Q over P. R is Q over P. And what would be S?